Thank you. It's great to be here. This is a bit of an experiment. This is a new talk. I finished it yesterday. I'm going to try and talk about two things at once, which is kind of on brand, as you'll see. And I'd love your feedback later as to whether that was interesting and helpful or just distracting and confusing. So I'm going to talk about product leadership, but I'm going to sprinkle it with a little bit of quantum physics. Bet you didn't expect that when you got up this morning. And the reason is that I think it'll hopefully provide a bit of color and give you a refreshing break from the incessant discussion about AI. Okay, so the story begins when I was preparing for a conference talk that I was asked to give a couple of months ago to an event that was focused on founders and investors. And I was asked to sort of represent the product function. And in the process of writing this talk, I found myself trying to enumerate the behaviors that I most consistently see in the highest performing product leaders. And I'm using leaders in the broad sense here. Everybody here is a product leader. And as you can imagine, I started just writing things down, and the list got longer and longer and longer. And then I started to realize that I seemed to be, in some cases, contradicting myself. Like many of the behaviors that I'd written down actually seemed to be explicitly in tension with other behaviors I'd already written down. And the more I thought about this, the more I realized this is not a mistake. This is actually an honest reflection of one of the core challenges of being a strong product leader, is the ability to be highly capable at a large number of behaviors that are actively in tension, but also critically to know when each of those behaviors is the right behavior to apply in a given situation to create the best outcome. And so, for example, the tone of a product team, the mood of a product team is often heavily influenced by that of the product manager. And so product managers generally need to be project optimism and positivity about the value of the work. But at the same time, they also need to be pragmatic about what could go wrong and plan for those possibilities and mitigate those risks before they hold things up. So the more I thought about this, the more I noticed that this really felt like superposition, like being able to hold these apparently inconsistent behaviors in your head at the same time and preserve them felt like superposition. And if you don't know what superposition is, I'm going to give you a quick lesson in quantum physics. So, back in the 1600s and 1700s, a debate raged in the scientific community about the nature of light. Is it a particle, a stream of particles, or is it a wave? And a key turning point in this discussion was an experiment that was done in 1801 called the Joule slit experiment. It was one of the most important experiments in the history of science. It's very simple. You get yourself a light source, ideally one of a single color, like a laser. You point it at a screen, and in between you put a plate that has two very narrow slits cut in it close together. Now, you might expect when you do that, that you'll just get two stripes, one for each slit. But actually what you'll see is this very distinctive pattern of dark and light lines. And it is not possible to explain that if light is made up of particles. It only makes sense if it's made up of waves, because waves diffract around those slits, creating these two circular wavefronts, which overlap. And when circular wavefronts overlap, as you'll see in this video, they create a very distinctive interference pattern, where different parts of those two waves cancel each other out or actually reinforce each other. And it's that same pattern that you end up seeing on the screen. So far, so good. So that settled that debate for about 100 years. And then Einstein turned up. And Einstein wrote a paper in 1905, one of his first papers, the paper that ultimately resulted him in winning the Nobel Prize, where he pointed out that a phenomenon that was previously not well understood, called the photoelectric effect, could be understood if light travels in discrete packets of energy. In other words, like particles. So, how do you reconcile that with the behavior of the Joule slit experiment? Well, let's see what happens if, for example, you tune your laser so that it only emits one particle of light, we call them photons now, one photon at a time. And what you would expect is what you see initially, which you just get individual dots of light appearing on your screen one at a time. But if you keep sending one particle at a time, eventually the same pattern comes back. And that's kind of weird. Like, how the particles know where the other particles went? What are they interfering with? Well, this is where it gets really weird, because quantum physics tells us that actually each photon is interfering with itself. Or to be specific, it's in a state of superposition. And superposition is this idea that you can have a state that is not well defined and that actually is multiple states simultaneously. So in the case of this experiment, the exact location of that photon as it moves from the laser to the screen is not well defined. It's smeared across all of the possible locations it might have between those 2 points. And it's only when it hits the screen, it's only when it's measured that it actually, we call it, collapses to one specific value, one of the values that it could have from across that range. So what's actually happening is that the probability that it turns up at a particular point on that screen is actually defined by its associated wave. And that wave interferes with itself, is subject to interference and diffraction just like any other wave. So you end up with this distinctive pattern. So the thing that's a bit strange is that the particle is effectively going through both slits at the same time. It exists in both locations, sort of probabilistically. So why is that? I should mention, if that just feels weird and doesn't feel right to you, don't worry, you're not alone. Even Einstein found this deeply uncomfortable. But the thing to understand is that superposition is a real phenomena. It is not just a mathematical trick. It's not just a consequence of us having inadequate instruments. It's a genuine effect that you can prove in multiple ways. And it doesn't just apply to light. You can run the same experiment with particles of matter, like photons or atoms, and you'll get the same result. And it's not just location that can be in superposition. Any property of a particle can be in a superposition state. So why is that a helpful metaphor? Or at least why did I kind of recognize that as a helpful metaphor when I was thinking about this problem? Well, it's because there are certain things that I think these behaviors have in common with superposition. The first thing is particles in superposition, when they collapse, particles in superposition can be in one of either states when they collapse. And similarly, it's important that you are able to adopt one of either states as needed, that you can be decisive or thoughtful rather than just decisive but not thoughtful. Secondly, it's also important to understand that when a superposition collapses, it collapses into one of those states only. It's not in a blend, it's not a mix, there's not a balance. Similarly, if you try and be somewhat, for example, somewhat decisive and somewhat thoughtful at the same time, you think that the best thing to do is walk the line in between, you'll end up being considered neither thoughtful nor decisive. So it's important that you are comfortable with the idea that you can be both very decisive and you can be very thoughtful, and you can be perceived that way by your peers without them even recognizing that there's a fundamental contradiction there. And lastly, it's interacting with your environment that causes the collapse of superposition in experiments. And the same is true here. It's only when a situation arises with specific context that you're forced to figure out in this moment in time, which of the different behaviors do I need to adopt for this situation to go well. Now, superposition is not just an interesting phenomenon. It's actually genuinely useful. It's the foundation of quantum computing. You may have seen pictures like this of a quantum computer. That is not actually a quantum computer. That is just a big fridge. All that does, that big chandelier does, is it keeps the quantum chip, which is that little thing at the bottom, very, very cold, specifically around 0.015 Kelvin. So Kelvin, a degree Kelvin is the same as a degree Celsius. It's just the scale starts at absolute zero, the coldest possible temperature. To put this into context, deep space is at 3 Kelvin, right, which makes these devices the coldest place in the known universe. There is no natural phenomenon that can create these temperatures. So if there exists anywhere in the universe anything that cold, then it's because some intelligent life made that happen. Okay, so quantum computers, essentially on that chip, they hold atoms, or there's various different ways of doing it, but let's say atoms in a state of superposition, and they use that to model what's called a qubit. And that's essentially, if you think of classical computers, they have their whole way of modeling data is through bits, right? And bits normally modeled using electric current can be either 0 or 1, and there are a set of logical operations you can perform on those bits. Quantum computers use qubits, and qubits have the weird ability to be both 0 and 1 at the same time. And they do that by holding that state in superposition. And I mentioned the logical operators here, not because I expect you to understand them, but just to help you realize that programming quantum computers is radically different than programming classical computers. It's a totally different approach to computing. Okay, so quantum computers are not general purpose devices. They're in some ways more similar to GPUs than CPUs. So they're particularly good at problems which really benefit from parallelism, or where a classical computer would have to exhaustively scan a large problem space. So for example, let's take solving a simple maze, or a complicated maze if you like, but this is a simple example. So maze is essentially, navigating a maze is about making the right sequence of choices between turning left and turning right. And if I overlay all the paths on this maze, you can see the points where you have to make that decision. And in this instance, there are 7 of them. So if I was going to try and solve this maze using a classical computer, yes, there are lots of optimized algorithms, but a very basic brute force approach that I could use is to just try every permutation of left and right at each of these 7 junctions. So for example, I could use 7 bits. I could say 0 means right, 1 means left, and then I could just count up. And I can count up and I can count up, because even this very, very simple maze, there are 128 different permutations, 2 to the power of 7. And you can see it's not until you get to the 92nd permutation that it finds the actual answer. However, a quantum computer, because it can hold each of those states in superposition, can evaluate all possible paths simultaneously and give you the answer orders of magnitude faster than a classical computer. Okay, so quantum computers have genuine potential value. It's still very, very early, though, in terms of the actual applications. Now, the way I think of it is we all have to navigate mazes every day, right? Mazes of stakeholders, mazes of strategy, mazes of deadlines. And these behaviors that we have help us navigate those mazes. And the trick, of course, is to figure out which behaviors are the ones you need in any given situation. Oops, double click, anyway. Okay. So, I mentioned earlier that the quantum computing industry hasn't actually settled on a specific way in which to model a qubit. There are lots of different ways of doing it, but one of the most common is to trap an atom and then use lasers to manipulate the energy of that atom. So basically, atoms have what's called a ground state, a lowest energy state, which is the most stable. But then if you shine a laser at them at exactly the right frequency, you can bump them up into an excited state. And so quantum computers use the ground state to represent 0, the excited state to represent 1, and then you can put the atom in superposition between those 2. And I find this interesting because people also have ground states. All those behaviors we talked about, all those pairs of behaviors, I bet you every single one of you, in fact, every person I've ever met, including the strongest leaders I know, have a bias towards one or the other. There's one state that you find most natural, that you find easiest, that doesn't require you to apply a lot of effort. And then the counterpoint to that is something you have to consciously work to do. So for example, if you're more introverted, then your ground state is probably to be more autonomous rather than more collaborative. If you want to be collaborative, you're going to have to expend a certain amount of energy to do that. And hopefully it goes without saying that it's incredibly valuable to be self-aware of your own ground states. Which of those pairs are the ones that you find most natural and most easy to do? And how much energy does it take you to really push yourself to do the other, to take the other position? Because if you do that, then you can really make a point of practicing those other skills, those other behaviors, in order to build a muscle and make it less exertive to do it. Okay, last quantum term, I promised, decoherence. Yes, this is the only AI-generated image. If you can find me a better one for the word decoherence, I'd love to hear it. The decoherence is one of the hardest challenges in quantum computing. Decoherence is the premature loss of superposition before the computation is complete. And superposition is lost because of interaction with the environment, and that can be due to any noise. So that could be heat, it could be magnetic fields, it could be vibrations. That's why these things have to be so cold. And just like quantum computers, we too can decohere. So when subject to our own noisy environments, when subject to the pressures around us, we can struggle to maintain the effort required to be in those higher energy excited states and just sort of revert to our default behaviors, our ground state. Another failure mode that it's important to be aware of is the possibility that we naturally tend to want to counter the behaviors of the people that we're associating with. So, for example, founders generally bias more towards the left hand, the green behaviors. And in that situation, you might feel as a product leader a responsibility to act as a counterbalance to that, and so respond with more of the red right-hand side behaviors. The problem is that if the company you're in values the green behaviors more than the red behaviors, as many startups do, this is not going to end well for you. Okay, so in summary, practice holding these conflicting behaviors in superposition. Don't be tempted to try and walk a line between them. Be very clear on which one you're adopting at any given moment and build intuition as to which will be most beneficial in a given situation. Be aware of your ground states, the behaviors that you default to, because you'll tend to overutilize those if you're not careful. Practice consciously adopting the behaviors that don't come naturally. And don't let stress or a desire to balance others cause you to decohere. Thank you.